So, ladies and gents, you guys did your reading on gravitation yesterday, and gravitation is a very interesting thing. Isaac Newton did a lot of work in terms of determining, really a lot of what we know we're learning in physics now, and he was able to come up with like the rules that dictate gravity, right, and this attraction because of mass, but he was never able to explain what gravity is. You know what I mean? So he was able to explain how it works and come up with relationships that will tell you how it works, but he was never able to actually say, this is what gravity is. Okay? And what he ended up coming up with is what you found out yesterday, or you read on perusal over the past week, was he came up with this thing called the universal law of gravitation. Okay? And the universal law of gravitation just says that two objects that have mass are going to be attracted to each other, and the relationship is going to follow this thing called the inverse square law, meaning as you get closer, right, there's going to be a greater attraction, and it's going to be the distance is going to be essentially squared. Okay, and the farther apart you get, right, it's going to be less, and it's not linear; it's squared. So if you're twice as far away, the attraction is now 4 times less. Okay. Someone asked that question in perusal, and unfortunately, I think it was Rachel. Unfortunately, it's one of these things where it's just, that's the way it is. It's one of those things in physics where you're just like, it's just the relationship that there is. Isaac Newton, a bunch of other people, I believe Cavendish was another one, performed experiments, right? And it always came out, the data always came out with that R squared relationship. Henry? Yep. Right. So, and we're going to get to all this as we go through. One of the questions, and there was a picture on it, it showed, I think Mira asked the question, why does the Earth essentially wobble as it rotates around the sun? It's because of the gravity act between the gravitational attraction between the sun and the Earth. It's the gravitational attraction between the Earth and the moon, right? So when let's say it's sun, moon, Earth, now you've got attraction of the moon pulling it this way in line with the sun, right? So that's going to pull you closer towards the sun. But when the moon is on the opposite side, now you have the moon pulling you one direction and the sun pulling you the opposite direction, you wobble back, right? But then you also have all these interactions between everything else in the universe. Some are stronger than others because of the distance away. So right now Mars is applying gravitational force on everything in the universe, but it's dictated by how far away they are. Does that make sense? It's a weird thing to think about. When you go into zero gravity, right? So let's say you go up to the space station, you're still experiencing all these gravitational forces, but it's a different reason why you feel weightless. And you read about it, and we'll get into it, okay? So he found this information right here, this relationship that has to do with this thing. Now G is just it's a constant. So what happened was everyone that did these experiments found that these two things change the same, but they're not the same number. Does that make sense? So they found like the force is this, and when we put the m1, m2 divided by r squared, they always changed in the same direction, right? So they were directly proportional to each other, right? But they weren't the same number, right? So it's not like this was 10 and these together made 10, right? There was always something that was being multiplied by it to cause it then to be equal to each other. And they found out that they call this thing big G, which is 6.67 times 10 to the negative 11, right? And it's Newton meters squared per, I believe, kilogram. Right. one thing that I was, in the reading that we did that I noticed is a lot of people got this G mixed up with gravity, okay? This is just a universal constant, okay? It's just a number that gets plugged in. It's actually not really related to lowercase g gravity, acceleration because of gravity. It is and it isn't, and we'll see in a little bit what it is, all right? So, you know, people ask, how come this number is different from like 9.8? Because they're not the same thing, okay? Does that make sense? Okay. So, yes? Probably, yeah. This is a super, we'll see in a second, this is a super powerful equation because this will allow you to find gravity at any point in the universe. This is why it's called the universal law of gravitation, okay? Anywhere in the universe, this equation will tell you what the gravity is, okay? Or what the force of gravity acting on you may be. So, you know, you're going to do a problem in a second, or a couple seconds, that we want to find out, like how fast the spy satellite goes around a planet, okay? And if you do one method, you get one answer. If you do another method, you get a different answer, and it has to do with this. Dan?
I was going to ask, is that constant throughout the whole known universe so
Yes.
far?
Yes.
So, what if we come up with something that doesn't have that true?
Then we'll have to change our understanding of it, but everything that we've done so far has said that G is that.
Do you think we even test it, or do you think we just assume?
Oh, it was tested.
I know, I'm saying, if we find something new, do you think we just assume it follows?
No, I don't know, honestly.
What if universe crashes into ours? Does it apply to the blobs?
I don't know. The blobs are theoretical. The blobs are theoretical. Okay, great. All right, so what I want to do is, and this was, so really everything follows this, and it was an interesting experiment, and it's always bothered me how they were able to do this and get an answer. But one guy, what he did was he took like two large metal spheres and put them near each other. And I don't know how you do it. Essentially, they hung, and he found that, I need to do research on it because it's going to bother me. Like two large metal spheres, maybe they're 10 kilograms each, so they're pretty heavy, right? But he found that they actually attracted towards each other when they hung near each other. I don't know how that distance was measured, because if you look at this thing, that's very, very, very small, right? If you have the masses here and all this stuff, the attraction is super small. Because if this is 10 kilograms, this is 10 kilograms, and you're still multiplying something to the negative 11, it's going to be really, really, really small. So I'm interested, curious about how did they measure that? No, just two metal spheres. No magnets, no nothing. Just, I don't know. Right. Yep. Right. Yeah, lasers could do it.
Yeah, where it started and then it. Yeah, and so
right.
The mirror turned so the beam went somewhere else.
Yeah. It's just. Yeah, it's very interesting. I don't know. Interesting. But the thing with this, so when gravity occurs, right, the weird thing is that if you're going to really experience it, it has to be massive, massive, massive objects, right? Planets, stars, solar systems, right? We have to talk about huge things, right? So technically, according to this equation, right, there is a force of attraction, right, between me and the board, right? But we can't feel it because it's so super, super small, okay? So, you know, we've got that going on. So first thing that I want to do is I want to look at how can we use this, if this is a universal law of gravitation, how can we use it to figure out the gravity wherever we may be, right? What is the acceleration due to gravity wherever we may be, okay? So let's imagine that we've got a dude standing on this planet A, okay? So if he's standing on this planet, right? What force is he experiencing just standing here? Gravity or weight, right? We call it weight. He's experiencing weight. going this way, all right, towards the center of the Earth, right, the center mass of the Earth, which we call in the middle, okay? So he'd be experiencing this mg. Now, we can call it mg, but he has mass, planet A has mass, so is this mg that he's experiencing, is it also the same thing as this gravitation force? Right? It's the same, okay? So what we can say then is that this mg that he's experiencing, right? And we'll call him just man, right? The mass of the man, right? So we can say that the weight that the man experiences is the same force as this gravitational force that he feels, correct?
Yeah.
Okay? So then, these are the same, right? So then all we have to do is plug in g. So now the acceleration that you experience because of gravity is going to be equal to g, the mass of the planet, right? Divided by r squared. And I made it big R because this is the radius or the distance they are apart. Okay? Now, if he's standing on the surface like we are, then this would be r, the entire radius of your planet. Okay? If we're talking about if the man is hanging out in space, right? Then r would be the radius of the planet plus whatever distance he is apart. Okay? Does that make sense?
Yes.
Henry?
So, the r is the distance in relation to center of mass.
Correct. Correct. So what this allows you to do now is you can find the gravity, right, the acceleration due to gravity at any place in the universe if you know the mass of the object and the radius of it. Right? So you could go to Pluto, all the stuff actually is in the back cover of your book. You can find out what gravity is in Pluto by just looking up the mass of Pluto and looking up the radius of Pluto. And it's in the back of your book. Pluto might not be in the back of your book now anymore. Let's say Neptune. Okay? So let's talk about how do we put something in orbit. Right? So how do we put a satellite in orbit? How do we put the space station in orbit? How do we get that to happen? Okay? So Einstein did a lot of these things called thought experiments, where he would just think about, okay, this would happen. And usually, and they were pretty good. They were a way to come up with it. Do you mind? So if we were on a tower, right, and we just shoot something at some sort of speed, horizontally, it's a projectile, correct? Okay. So when we shoot it out, it's going to come and eventually it's going to hit the ground, correct? Make sense? Okay. Now, if I shoot it faster, right, it's going to come and it's going to slowly be pulled down by gravity, and it's going to go a little bit farther, right? Sorry. I'm just labeling them. Okay? So we shoot a little bit faster, it's going to continue to fall towards the Earth, right? If we shoot it even faster, it's going to fall towards the Earth until maybe it hits down here, right? But if we can shoot it at a fast enough speed so that as it falls, it matches the curvature of the Earth. Does that make sense? So as it falls right here, as it's matching the falling radius of the Earth's curvature. If we can shoot it fast enough, it would eventually fall around the Earth. So, when you go on a roller coaster and at some point you feel like you're weightless, right? Because now you're falling essentially at the same acceleration as Earth. Okay? That is what happens when you're on a space, like on a space station or you're out in space. There is still gravity, right? There is still all those things for gravitational forces acting on you, and you can experience that, right? But the reason why you feel weightless is because you're accelerating at the same speed as everything around you, right? Because what you feel weight is really that normal force acting on you, correct? Does that make sense? So you feel weight because the floor is pushing up on you. But if everything is accelerating at the same rate, so if the space station is accelerating at 9.8 and you're accelerating at 9.8, right? Everything's accelerating together, you don't experience a normal force. So that's why you feel weightless. Okay? So what you're doing is, you go out in that space station, it's zinging around, it's falling, essentially it's in a constant state of free fall as it goes around the planet. Okay? And you have to go really, really fast to do that. In our textbook, not the perusal book, the textbook, they do a little calculation, and imagine that if you were on the surface of the Earth and the Earth was completely smooth, no mountains, trees, anything like that, and there was no air, because air will provide friction, which will slow you down, you'd burn up. If you were able to be shot as a projectile to fall around the planet and just skim the planet, the surface of the planet, so your radius is essentially just the radius of the planet, you'd have to be going about 18,000 meters per second. That's crazy fast, right? Crazy, crazy fast. Let me just make sure that that's the number.
At what point was the gravity sign?
I'm sorry, it's about 18,000 miles per hour. Slightly different, right? It's about 8,000 meters per second, 18,000 miles an hour. That's how fast you have to go to just skim the Earth and go around and orbit the Earth. Right? They're not that extreme. Okay? So here's what I want you to do now. You're going to take a couple minutes, right? You can work with a partner, work with your table mate, all right? We have a planet, right? And all right? Shh. Ladies and gents, so we've got this planet, right? And obviously, clearly not to scale. All right? And I want to launch a spy satellite, right? I'm going to put it in essentially what they call low Earth orbit, okay? So what I do is I've got my planet here of radius r, right? And it is a distance d away from our place, okay? Know what I'm saying? Okay, or a distance away from d away from the Earth, where we know that the radius of the Earth is 6,300 kilometers, right? And we know that the mass of Earth is 5.98 times 10 to the 24th kilograms. And the distance away is 350 meters. And I would like to know, if we're going to keep our spy satellite so we can spy on people and things like that, right? I would like to know, how fast does my satellite need to orbit Earth at this distance away to keep it in stable orbit? Does that make sense? Okay? All right. I'll give you a couple minutes. All right, 1 second. What's the free body diagram for our satellite? So it's gravitational force? Anything else? That's it. Okay, so what type of force is this?
Centripetal.
Centripetal force. Okay. Let's find out how fast this thing is going, right? How fast does it have to go if we're going to keep it in that orbit? All right. So our free body diagram shows that the only force that this satellite should experience is that gravitational force attracting it in there, right? And that's creating a centripetal force, right? Because it's trying to go around the circle, and the force is directed towards the center. I'm just going to clear this up a little bit so that I have a little bit of space to write on, and that should be kilometers. So if we look at this, we can start with Newton's second law, right? Everything, whenever we deal with forces, it always goes back to Newton's second law, okay? And if we look here then, the only force it experiences is that gravitational force, and it's causing a centripetal acceleration. Correct? We're good there? Okay. Now, this gravitational force that it's experiencing would be G, m of the satellite, m of the Earth, divided by, we'll call it, I'm just going to call it r plus d for now. Does that make sense? Squared? Okay? And that's equal to m of the satellite times v squared over, I don't like using this notation, but we'll do it for now, r plus d. Does that make sense? Okay? So if we look at it then, one of these goes away with that. Okay? The satellite's masses go away. So we get v squared is equal to g, mass of the Earth, divided by r plus d. Correct? So that then the speed with which this thing needs to go around is equal to the square root of big G, mass of the Earth, divided by r plus d. Follow me? Okay. So then if we're just plugging things in, sorry, I'm flipping through everything like this. G is, I believe, 6.67 times 10 to the negative 11. The mass of the Earth was
5.98 times 10 to 24.
Times 10 to 24. Okay. Divided by now, oh, we said 350 plus 6,300, right? So 6,650. Correct? So 6,650, and then 1, 2, 3. That would be your radius, right, in meters. Correct? Okay. And then, so the speed needs to be, did anybody get this number?
7,745.94 meters per second.
All right, so we'll call it 7,746 meters per second. Okay? Now, hearing your conversations, it sounds like some of you, instead of doing like the G m1 m2 over r squared, some of you just do mg. Some of you do mg instead of that whole m1 m2 thing. Yeah? So did someone get a number other than this? Maybe a little larger, closer to like 8,100.
Oh, I did it right.
Okay, so that is actually it's a good spot. It's like it's a good catching point that may trip you up. If you had done mg instead of this g, the universal law of gravitation, you would have gotten a different number, and that number would be off because you're so far away that gravity is not 9.8 anymore. Does that make sense? Right? Which is kind of cool. That you're that far away that now gravity is not something. I think, Henry, did you calculate it? 9.02.
Yeah.
That makes a big difference. That's a difference if you did it out as 9.8 instead of 9.02. That's a difference of about 400 meters per second. That's a lot, right? Which most likely means that you'll be probably a little closer in at that speed, right? Or actually, you know what would actually happen? If you were 400 meters per second too fast, you would swing around and then whoosh. Peace out, Earth.
Never to be seen again.
That's how, when we send satellites and things out to other planets, we will do that. We will put them into orbit around another moon, a moon of a different planet or another planet, and use this gravitational force to speed us up, to fire us out. So like when we send things to Mars, or we send things to other planets, like, there's New Horizons went out to Pluto, right? We whipped it around Moon before we sent it around there to get it up to speed. It's essentially almost like free speed. We don't need to use like boosters or anything like that or any fuel to get it there. We'll just put it into the gravitational field of a planet or a moon, and we'll put it too fast. We'll use it to speed it up to get it too fast so it can't stay in orbit, so it gets slung-shot out to go wherever it needs to go. It's almost like, it's not free energy, but it's energy that we don't have to expend or carry.